Morning, everybody. Welcome to ABL's market briefing here at the Old Library at Lloyd's for May 2026. My name's Mark McGarren. I'm the Global Managing Director for Maritime here at ABL. Our briefing this morning is accredited by the Chartered Insurance Institute, and delegates can claim up to 1 CPD hour for your participation. We'll therefore keep a record of those of you in the room today and those of you logging on online. If you haven't already done so, please make sure to sign in with us after the briefing in order to receive your follow-up email and CPD accreditation. Just a quick reminder today as well, we will be ending the webinar portion of the briefing after the technical presentation, and the maritime casualty reports moving forward will only be presented in person at Lloyd's. Of course, we are happy to discuss with anyone who would like more information on them post-briefing and look at how we can make that data available to you, so please contact us afterwards. I'm delighted to introduce our technical speakers today. Kevin Williams, Marine Engineering Director at ABL London, will be doing the technical part of the presentation on hydrotreated vegetable oil as a transition fuel going forward. And to read this month's case report, we welcome back Oliver Tattershaw. Oliver is a naval architect here at ABL and part of our graduate programme. Thanks for joining us again. The usual caveats apply, Chatham House rules apply. The information in the presentations and the opinions or comments expressed are those of the presenters and not necessarily those of ABL. At the end of today's briefing, can we please ask everyone to take 3 minutes out of their time to complete the online survey? This is a critical element of our CPD accreditation status, and we want to be able to continue to offering that opportunity to you to get 1 CPD hour per briefing. It also means we can actively look how we can improve these briefings to match your requirements and needs. Thank you. You can download the QR code from the screen, and we'll also pop it in an email on the follow-up as well. As many of you I'm sure are aware, we are closely following the conflict in the Middle East, and we're deeply saddened by the tragic news of several deaths of seafarers already as a result. We all know in normal circumstances, seafaring, though a critical occupation, can also come with risks. Obviously, our thoughts are with the departed and their families and friends. But I also want to draw attention to a further, I think the IMO reported around 20,000 seafarers impacted in the region. As many of our own staff, including myself, come from a seafaring background, we take our commitment to support seafarer well-being very seriously, and we support Stella Maris along with other seafarer charities in their important work in this area. We're also a signatory to the Neptune Declaration on Crew Change, which, although it was a COVID initiative, is still important today. And you can become a signatory to this, and perhaps we might see some developments or new policies come from in light of the current situation. If you'd like to donate to Stella Maris, there's a QR code here on the screen, as well as one outside. And I'm sure anything you can spare will be of great help to them. Oh, right. Okay. Sorry. Now I'm going to welcome Kevin Williams to the stage. Thank you.
Thank you, Mark, for that introduction. Welcome, everyone, and thank you for attending and taking time out of your day. My name is Kevin Williams, and I'm the Marine Engineering Director at ABL London. I've been with the company 5 months now. I'm a chartered engineer and a member of the Institute of Marine Engineers and Scientists and Technologists. I've had a certificate of competence, Chief Engineer's certificate of competence with the Maritime Coast Guard Agency for 20 years. And I've spent 17 years at sea, 5 of them sailing as Chief Engineer. And in 2011, I decided to come ashore into the technical management side of shipping. On the screen at the moment is a variety of the ships that I've both sailed on and also managed. My experience is generally with passenger general cargo, small cruise vessels, ro-ros, ro-packs, high-speed craft, marine aggregate dredges, and more recently, oceanographic research ships. So today, we'll be exploring hydrotreated vegetable oil, or HVO, as a practical transitional fuel to reducing emissions from specialist ships. The reason I said specialist ships because most of my research was done on oceanographic research ships, but I do believe it's suitable for other specialist ships like dredgers and those type of vessels that are not actually on a regular trade. The presentation hopefully will draw on some real vessel trials and industry research. For the last 7 years, I work for a UK Oceanographic Research Institute, and as part of my role, I was required to deliver carbon reductions by 40% by March 2025 and net zero by 2040. I left before 2040. The only way we were going to reach 40% of reduction by March 2025 was to use an alternative fuel, and that's why my focus has been on HVO. In addition to that, I was completing an MSc in Sustainable Maritime Operations with Plymouth. So at the time, I combined the two tasks of work and study. The 5 key learning objectives we'll cover today. You should be able to explain the drivers behind maritime decarbonisation, assess why zero emissions vessels aren't yet feasible across all sectors, and describe what HVO is. Hopefully, we will also evaluate the technical, operational, and environmental performance of HVO and understand some of the implications for the marine insurance. The climate and shipping problem. Well, the climate problem, it can be argued that human-driven CO2 emissions are altering the climate and the oceans, with changes in weather patterns, seawater temperatures, all linked to global warming. Shipping, as can be seen from the diagram on the screen, plays an important role in contribution of emissions. While shipping only accounts for 3% of global greenhouse emissions, it represents 11% of transport emissions, and transport itself represents 22% of the total global CO2. Global trade. The shipping sector cannot be ignored and replaced, with around 90% of global trade being conducted by ships. And the demands are increasing, so too will the emissions. The need to change. Why we need to cut emissions and act on climate change. Well, CO2 is the main gas causing global warming, and ships being pushed to cut their emissions. Many organizations have set net zero goals, so they must change how they buy and plan their fleets going forward. Stronger rules from international groups, governments, and ports. The IMO wants to big cuts in greenhouse gases and want to be net zero by 2050. In Europe and other regions, new rules such as Fuel EU Maritime and port requirements for shore power are increasing. Ports and emission control areas have stricter local air quality limits, not just on CO2, but NOx, SOx, and particulate matter as well. Money, funding, and customer expectations. Well, carbon taxes and levies, fuel standards, and other compliance costs are more likely to be a bigger risk. Fossil fuel prices are uncertain, and so organizations are looking at hybrid and alternative fuels to reduce those risks and costs. Reputation and living up to our mission. The research organizations are expected to run their operations in a way that matches their environmental goals. At the research institute that I worked at, it was no good we going around and telling people what we should be doing for the maritime industry, yet doing the same ourselves. So that's why there was a big push on decarbonisation. New technology, batteries, hybrid systems, fuel cells, cleaner fuels like ammonia and methanol, and port electrification are improving fast, making low carbon shipping more practical. Just touch briefly on the IMO strategy 2050. It's fairly self-explanatory. The short term, reduce fuel consumption, more efficient vessel design, power limitations, propulsion aids, and the use of biofuels. Also, conversions to LNG and methanol. Longer term, replace carbon-based fuels like HVO and MGO. Alternative carbon fuels must be adopted, like hydrogen, ammonia, nuclear, and battery power from renewable sources. Interestingly, on the short-term list, we have LNG and methanol mentioned. it is carbon-based, so it doesn't meet the long-term objective. And so that's why IMO's put it in the short-term column. The diagram above illustrates what IMO think are the full ranges available to decarbonisation. As you can see, some of the measures are layered. There is no single solution for hitting the 2050 target. The area that I've focused on is the biofuels, which is predicted to be about 90%. So going on to zero emissions vessels. Well, when we talk about zero emissions vessels, we need to explain there's a distinction between tank to wake and well to wake, or life cycle zero. Tank to wake means there's no CO2 SOx or particulate matter at the exhaust, and then ideally no nitrogen oxides as well. This is what most people mean by operationally tank to wake zero emissions vessels. Well to wake life cycle zero includes upstream emissions. This is harder and depends heavily on how the electricity or hydrogen and ammonia are produced, and it's far more difficult to have that traceability. A true zero emissions vessel must consider three factors: the energy carrier, the prime mover or conversion technology, and the propulsion and onboard power management systems. If we take the energy carriers to begin with, battery electric vessels, they are true zero emissions vessels. Best fit for short sea ferries and inland coastal and predictable routes. The key limitation, though, is energy density and the range, weight, and space. Plus, charging infrastructure and grid capacity is not matured sufficiently at the moment. Hydrogen. If used in the fuel cells, the vessel exhaust is essentially water, though emissions depends on where the hydrogen source originated. The challenges with hydrogen is storage, volume, compression, safety, bunkering availability, and the cost of green hydrogen. Ammonia, no carbon. In ammonia, there's no carbon molecules, so potentially CO2 free at use. The challenges, though, are toxicity, safety and training, NOx control, engine maturity bunkering, and regulations still need to develop. And finally, not a whole vessel solution, but shore power or cold ironing, zero emissions in port depends on the port infrastructure and electricity carbon intensity. For the prime mover and the conversion technology, you have battery to electric motors, fuel cells, or combustion engines adapted for new fuels. For the propulsion and onboard management system, the focus is on electric propulsion, hybrid systems, hotel loads, and redundancy. The critical challenges for zero emissions vessels. Well, fuel supply and refueling. The right fuels and ports are not available everywhere yet. Rules and approvals, regulations and ships approvals are still changing. At the moment, the rules and regulations are lagging behind where they need to be, mostly because flags and class are learning the same lessons that we are learning as we promote sustainable shipping. Space and range. New fuels and batteries can take more space and reduce range compared to today. Costs and uncertainty. Big investment decisions are hard, and while standards for winning fuels are not clear, there is a cost associated with uncertainty. The research that I conducted concluded that zero emissions vessels are not feasible within the next 5 to 10 years for oceanographic research missions. On the zero emissions vessels as well, what are not considered, biofuels and HVO can reduce life cycle CO2 significantly depending on feedstocks. but they still emit CO2 at the exhaust. And so they're typically a transitional fuel rather than a zero emissions pathway. LNG can reduce some air pollutants, but methane slip and life cycle greenhouse gases concerns means it is not considered for zero emissions vessels. Moving on to biofuel. What is a biofuel? Well, biofuel is any fuel derived from biomass, which includes plant materials, algae, or animal waste. This concept is not new. Wood has been burned for years throughout human history for energy. Modern biofuels include ethanol from sugarcane and corn, and biodiesel from plant oils like soybean and oil palm. Biofuels have a longer track record in aviation and road transport than in shipping. Bioethanol and biodiesel blends have been in use since 1970s, and bio-based jet fuel was approved in 2011. Marine applications started later with soybean biodiesel feasibility study for recreational boats in the Great Lakes around 1998. There's four main categories, and I know there's only three on the screen, but the four main categories for biofuel relevant to our discussion are biodiesel, known as fatty acid methanol esters. They're produced from vegetable oils and animal fats. This is widely available type of biodiesel in the industry and is often blended with regular marine diesel. Fane diesel blends with up to 30% content and is used in automotive applications and referred to sometimes as B20 or B30. Biogas or biomethane is produced using the whole plant or organic residual and waste materials. Methane is produced in a fermenter of a biogas plant through biotic reaction in the absence of air. And bioethanol comes from alcoholic fermenting and subsequent distillation of sugars, starch, and starchy plants. It can also be produced in the chemical process of reacting ethylene with steam. And of course, the fourth one is HVO. HVO is a renewable paraffinic diesel fuel produced by hydrotreating vegetable oils, animal fats, and waste deprived from oil, usually waste cooking oil. It is generally presented as a drop-in substitute, which means it can be just used as if diesel and substitute for mineral diesel. It's often introduced into existing diesel storage and fleet operations with limited change. It is virtually colorless and odorless, like water, but creates problems for engineers, which I'll touch on briefly. HVO is made from treating oils, fats, and waste-derived feedstocks with hydrogen at high temperatures and pressures in the presence of a catalyst, producing stable diesel range fuel. The process removes the oxygen from the molecules and create paraffinic hydrocarbons, straight branch chains that perform similarly to conventional diesel. It also produces byproducts such as propane, which can be recovered and reused. Because HVO is close to fossil diesel in performance, it can often be distributed through existing diesel supply chains, provided it meets the relevant fuel specifications. This differs from fane diesel, which is used using methanol and retains oxygen in the fuel molecules. Key characteristics of HVO. So chemically similar to fossil diesel with a high cetane number, sulfur and aromatic free, reducing SOx particulate matter. Very good coal flow properties, making it suitable for climate both climates and marine operations. Some of the trials that we conducted in my previous company worked with ships in Antarctic, and they had no issues with the fuel and the stability. Compatible with existing marine diesels and auxiliary equipment. Most of the trials was conducted using the main engines, but on board a ship, you do actually have other auxiliary equipment like lifeboats, emergency generators, and the fuels were not tested on that. So that's something that has to be done at a later stage. Feasibility and performance. Technical viability. HVO can be used in most engines as a direct replacement for marine gas oil with little or no changes needed. The environmental benefits, it cuts CO2 emissions by 90% and reduces NOx, particulate matter, and sulfur. HVO does produce CO2 and NOx and SOx, but because this has been accounted for in its previous life as vegetable oil, and so it's termed net zero, it does actually produce CO2. Economic and supply challenges. HVO is usually more expensive, about 1.3 to 3 times the cost of marine gas oil, and supplies are limited, and sustainability depends on how it is made. Short-term emission solutions. Overall, HVO is a useful short-term way to reduce emissions. And while zero emissions vessels and port infrastructure is still being built, it seems an obvious choice. The challenges with HVO. HVO has a strong potential as a transitional fuel, but several barriers may limit its widespread use. The high production costs and limited availability, the sustainability concerns, and feedstock origins. Hydrotreated vegetable oil doesn't have to be certificated. It is actually voluntary certificated. And this introduces other factors. ISCC in Germany do actually certify HVO, but it doesn't have to be. The lack of mandatory sustainability standards worsens these challenges. To unlock HVO's potential, there's an argument that there needs to be more coordinated global action, including stronger certificated frameworks, expand production capacity, and improve distribution networks. The diagram above identifies other challenges using biofuels, and trials with the HVO looked into the following. Stability and storage properties. Under trials, there was no problems with stability or storage properties. The reduction of moisture and oxygen in the fuel means it's more stable than any other biofuel. Potential microbial contamination. Again, microbial contamination depends on moisture, oxygen, and with the removal of that, it's potentially non-existent. Lubrication properties. Lubricity. Most all low sulfur fuels have a problem with lubricity. However, the challenges with HVO is exactly the same as any low sulfur fuel. There is no difference. Deposits and temperature properties. Again, there was during the trials, there was periods at the beginning where HVO had a cleaning effect on pipework, and so this debris ended up in filters. So there was an increase in filter blockages originally, but once those pipes are cleared, they were back to normal. Corrosive and acidic properties. Less corrosive than some of the other biofuels, but there's also a consideration to be had here. The other thing about the trials is that there is no long-term effects on engines, something that only the use of HVO will determine. Impact of HVO on the insurance market. Well, The risk profile compared to conventional marine fuels. HVO is chemically very similar to conventional marine distillate fuels such as MGO. It is non-toxic, has a high flash point, contains no sulfur or no aromatics, and behaves in a predictable manner during storage, bunkering, and combustion. The hazard profile of HVO does not materially increase traditional marine risks such as fire, explosions, or pollution, and compared to existing fuels, it very much remains the same. HVO is therefore viewed as a low-risk transitional fuel rather than a novel or experimental one. The machinery and operational risk considerations. Although classed as drop-in fuels, the trials supported literature identify that operational considerations that insurers will pay attention to, including increased fuel filter and purifier blockages, potentially higher lube oil consumption, minor changes in the combustion characteristics, such as later ignition and slightly elevated exhaust temperatures. Fuel quality and certification and the moral hazard. One of the most significant insurance-related challenges with HVO is fuel provenance and certification. Sustainability schemes such as the ISCC are currently voluntary, and not all marketed HVO is subject to these uniform standards. From an insurance perspective, this introduces fuel quality risks if off-spec or contaminated fuel leads to machinery damage. Moral hazard risks where sustainability claims cannot be independently verified. Pollution and liability exposure. HVO is a biodegradable, non-toxic, and produces low particulate matter and sulfur emissions than fossil fuels. As a result, the pollution liability exposure is reduced rather than increased, particularly in the sensitive marine environments. For P&I clubs, this is a positive attribute as it aligns with tightening of environmental regulations and port state control expectations. Regulatory and transitional alignment. The market is increasingly sensitive to transition risks, particularly assets that may become non-compliant in future regulations. HVO aligns well with IMO decarbonisation goals and initiatives such as Fuel EU Maritime, without locking the owners into a long-term, high-risk technology pathway. Premium and market impact. In the short term, HVO use is unlikely to result in premium reductions, as insurance prices still mainly reflects hull value, claim history, trading area, and vessel conditions. So summary, HVO is a drop-in fuel, so it can be used in all engines with little or no changes. Tests show HVO performance like marine gas oil. There's small difference, slightly higher exhaust, more lube oil consumption. HVO can cut CO2 up to 90% and reduces NOx, SOx, and particulate matter. Downsides is it costs considerably more than MGO and is not available everywhere, and its green impact depends on where the feedstocks and hydrogen comes from. Overall, HVO is a good short-term way to lower emissions, while truly zero-emissions fuels and port infrastructure is still being developed. The simple conclusion is HVO can reduce emissions using today's ships, but to scale it up, the industry must improve supply, bring down costs, and make sure the fuel is produced sustainability and certificated. HVO works best alongside efficiency upgrades and hybrid systems while we prepare for full zero emissions shipping. This is a quick walkthrough of the problems. CO2 is a major contributor of greenhouse gas. Shipping is a significant emitter of CO2. Shipping is still going to play a significant role in global trade, and the need for ships will increase. Zero emissions vessels will provide the answers to emissions from ships, but it's not going to be available in the immediate future. Alternative fuels are part of the answer to reducing greenhouse gases, but no one fuel type is superior, and the others, which is causing indecision with original equipment manufacturers. So hopefully this presentation covered some of the learning objectives set out. Thank you for your attention, and if you have any questions, I'll happily take them. So it's one of them.
So yeah, you see that ABL it's from transition, but when you say it's given a zero carbon negative based utilizing stays on everything. You see it on a carbon recycling pattern to help us in the solution. And you envisage issues over being able to produce the quantity of oil from conventional oil bearing crops here at HCO, that sort of thing. To be able to put a greenhouse needed which is.
Yeah, so there's quite a few questions in that. So I'll take the first one, which was the fuel is the carbon is accounted for in its previous life. Yeah. So do we see this as a long-term solution going forward? No. HVO is being used in public transport as we speak, and there is a big push for HVO in public transport, but not in the maritime industry at the moment. I think mainly because if the maritime industry decide to buy up all the HVO, that will certainly push the price up. There is limited availability. There's only a certain amount of stock of HVO and original crop. Going back to growing our own, I think that's what you mentioned. Yeah. So I think at the moment, and that's my personal thought, is that we have to get what we're doing correct first. There is no regulations involved in that. So there is no reason why deforestation and palm oil cannot be introduced into these feedstocks, which goes against the whole idea of sustainability. So I think until we get certification sorted, it's highly unlikely people will invest in HVO until those regulations are tightened up. I'm trying to remember the other part of the question. Sorry.
So oil and crops in yes.
I do think we should be doing more locally, because at the moment the feedstocks are coming from Southeast Asia. It's being refined in the likes of Singapore, and then it's being distributed to Finland for use in Europe. So I do think more localized feedstocks will help that. I think there's a big infrastructure to put in place first. So in the short term, I think we should be able to do some more research into that anyway. Thank you.
6 for to use it because it's expensive, hard to get, doesn't affect premium, understanding. Then where's the
where's the incentive to use HVO given the reasons I laid out, costs the availability and everything else. So regulations. When I said specialist ships, you do have a fishing fleet that will not be able to meet the regulations eventually. They're normally owners who doesn't have the money to invest in new fuels and new engine equipment. You also have marine aggregate dredges that are operating. I don't think there's an incentive to use it at the moment because it's taxed. The only reason I see that there might be a possibility is if there was a charter that someone specified that they needed. I'd like to have my charter done relatively net zero, and that would be the only reason why you would be using it. I think the expense is the big problem and availability. So yeah. Hopefully I answer it, but not like, the regulations is going to push us in down that route. Thank you.
Mark Shipley with Marsh. So it's really a supplementary question. So we heard all the downside on that, and we're talking about supply chains are a major issue, prices are a major issue, blah 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 blah. Are there other routes to overcoming that somewhat that don't need not necessarily bring the same level of environmental or CO2 benefit, such as can it be mixed with biodiesel? Are there other production routes that you can go down that don't get necessarily dependent on waste cooking oil? You briefly mentioned use of palm oil.
Yeah.
Are there other routes to overcome the supply chain issue? I'm sure price is all different.
Yeah. Yes. So there is other options. Feedstocks, different variant feedstocks, but it goes back to certification. I think you got to know where those feedstocks are being sourced and located, and then you can sort of monitor the process right through. Sorry, there was one thing you just touched on earlier.
So it's not.
Sorry.
When the companies are nothing.
Yes. Yeah. Sorry.
Use the CO2 benefits, if not necessarily the entire using 100% HVO.
Yeah. I remembered. So the HVO can be blended with diesel to give you. It doesn't have to be pure HVO. It is compatible to be loaded with diesel, and you do have companies that offer that benefit. So you get a B50 or a B30 diesel. Alternative routes, I think it's mainly. It's hard to promote HVO when you have all the challenges that you've got. But it was for the purpose of my research, we hit 40% reduction by 2025, which was the initial target. But it's one of those strategies that you hit that target. What are you going to do now? And that's where we are. Sorry. Yeah. Oh dear.
If HVO is used and next time, so set point of bunkering, HVO is not available, can the engine use the conventional fuel again?
Yes. Yes. So part of the trials that we conducted, for example, we loaded HVO in the UK. The ships that I operated went down to Chile, Antarctica, and everything else. You cannot get HVO. Well, you can, but not sustainably sourced or controlled. So in those countries, we ended up getting MGO again. So yes, you can transfer backwards and forwards between the two wherever the supplies are.
This. You can find this, how far away do you think we are from next straight dimension?
No, I couldn't answer that. No. That's it. Thank you very much.
That is the end of our webinar. Thank you for joining.